Good morning, and thank you for your interest in attending this presentation. I'm going to talk to you about the quasi-steady Lagrangian coordinate structures in the Mediterranean and Iberian Atlantic waters. The Lagrangian coordinate structures basically are material lines that organize the fluid flow transport. Here you have an introductory paper in Physics Today, but briefly we can say that attracting LCS take the form of material line that plays the dominant role in attracting neighboring fluid elements onto itself. Okay? For instance, here we are presenting a case. This is the Guadalupe Island. The wind comes from the left, and this is the clouds. This is not the ocean, it's the atmosphere. And we see how the presence of the island creates zones in which the clouds are very concentrated. These lines are attractive lines that attracts clouds and are the LCS. Okay, are LCS. LCS cannot be crossed by material or barriers, and can be relevant to study the pollution transport in the ocean, or also the larvae distribution, or to help in search and rescue tasks. In particular, we are interested in those lines that have the highest local rate of attraction in this case. Okay? How the LCS can be computed? Well, there is a lot of information in papers and something, but here I have included two of them, okay, that you can consult to go further in this topic. But basically is based in the local deformation of the fluid, how the fluid is deformed. And here, for instance, we have a point. In this point, this central point, we can compute the Cauchy-Green deformation tensor for this example of this velocity field, and we see how a fluid element located here will travel towards this point. And in this travel, the fluid is stretched in filaments. Okay, this direction is the second, is one of the defined by one of the eigenvectors. This direction is an attractive direction, whereas the other is a repulsive direction. Okay, then here we can define the direction, the repulsion and attraction directions. Okay, the repulsion and attraction rate also is related with the eigenvalues. Okay. Here, if we integrate along the first eigenvector, we will find the repelling LCS, and if we integrate along the second eigenvector, we will find the attracting LCS. Okay, integrated forward in time, we will find the repelling or the attracting, and we need to put as local as a starting condition to integrate that the local maximum of these eigenvalues or local minima for this one. Okay, we define local maximum, then integrate along this line. We will find the highest or the Lagrangian coordinate structure that has the highest rate of repulsion. On the contrary, if we put the condition of local minima of the first eigenvalues, and we integrate along the second eigenvector, we will find the most attracting Lagrangian coordinate structures. The climatologic Lagrangian coordinate structure has been defined by Rodrigo Duran and collaborators in this paper, and they provide a MATLAB source code to integrate them. It basically starts from the climatological velocity fields. Okay, then it is possible to compute the monthly Cauchy-Green components, and then to solve the ordinary differential equation to find the Lagrangian coordinate structures. Okay, we have performed this computation with 4 different products. One of them comes from altimetry. The other one is altimetry plus Ekman component, and the other is the hydrodynamical model and sea level assimilation. The fourth is provided by HACOM. Is a global product of HACOM. Okay, and this is the typical map of the Lagrangian coordinate structure in the surface. Okay, we see how the main currents and gears are associated with a very high attractive lines. This is the red lines are the more attractive lines, and we can see how these lines act over a freeze component. Okay, we see here in January and August how or what is the evolution of the same set of particles, okay, along the time. We see how these lines act as a barriers. Okay, here are not strictly barriers because these lines are climatological. Is in some sense is the mean of this month, and is not the instantaneous Lagrangian coherent structures. But we see how they are dominating what is the dynamics of the fluid. Okay? Well. Okay, well, very fast. Here we have the vorticity, the different behavior of the products. First of all, globe current provides a Lagrangian coherent structure very weak. Okay, are very weak. Sea level provides a low seasonal variability. Then both we won't show any result with both of them in this presentation. The wind effect, we see how the wind effect is very clear on the climatological Lagrangian coherent structures. For instance, in the northern current here, we see how it associates attracting lines. Okay, this is November, and also the Algerian current. But in July, when we have the Mistral wind and the Levant wind here, we see how the structure, the wind breaks the attractive lines. Okay. Also, in the Aegean Sea, the Multemi wind in July also introduces attracting lines in the leeward part of the island. Okay. Then all the materials such oil spills, plastics, etc., will be attracted leeward in the presence of islands. Also, the distribution of larvae is very conditioned by these structures, because, for instance, here we have two plots from the work of Aristegui et al. In this work, they see, for instance, that in July of 2007 there are some zones of dispersion, the green, or retention, on the orange, retention of larvae. Okay, and these sections, these regions coincide very well in the case of the climatologic Lagrangian coherent structures, because when we have strong structures parallel to the coast, these act as retention zones for the larvae, and when we have a perpendicular lines perpendicular to the coast, this zone acts as a dispersion zone for the larvae. Okay, for instance, here we can see the evolution of some material, in this case larvae, put in the surface. Okay, the stars here, and here at 15 meters of depth. Okay, we see how this part acts as a dispersion zone. And well, the conclusion is that the validation is going on, but preliminary tests suggest that the study of climatologic Lagrangian coherent structures can be a valuable fast decision tool in cases of marine emergencies. The monthly Lagrangian coherent structures surface map allows the identification of regions that can contain high concentrations of drifting objects like plastics, larvae, etc. And from the studies product, the HICOM and C products are the most promising to describe accurately enough some of the mentioned fluid flow transport. Okay, then thank you for your attention, and that's all. Thank you very much.